My name is Jeremy North. I'm the chairman and one of the founders of the Liquid Air car, the Dearman engine company. I'm going to show you a short video which introduces Peter Dearman, who is the slightly eccentric 60-year-old inventor of this technology in his shed in Bishop Stortford, just north of London. And because of this slight eccentricity, the BBC got interested and decided to do a short piece on it.
Just pour some in there.
Take a bucket of liquid air, chilled to minus 190 Celsius.
That'll do.
Allow it to warm and turn back into a gas. If you fix a tube, the liquid air will expand and rush up the tube to turn a motor.
It's boiling now.
It's been developed by a lone inventor, Peter Dearman.
Well, obviously this is the smallest one. I just used this demonstrating to people, to show them the technology. And then I went up to a bench prototype, and then I thought, well, I better do a car because that's much more impressive. And that's when I did the car.
And here he is fueling up the car with liquid air again. It runs round the streets of Bishop Stortford in Hertfordshire. Mr. Dearman's been working on the idea of liquid air motors for more than 40 years. His laboratory is his garage. It's strewn with liquid air motors.
This is the first one, which was a modified lawnmower engine.
Now this backyard gadget man is being taken increasingly seriously by the scientific establishment. Especially since a power station in Slough came up with another use for cold liquid air, storing energy from electricity produced by wind farms in the middle of the night.
In the coming decades, we have plans in the UK to bring large amounts of wind-generated electricity onto our system. And the challenge there is that the wind only blows at certain times of the day, and we need to be able to store that electricity for times when the wind is not blowing.
The liquid air system may offer one option for that power storage.
There's another innovation here. The liquid air process is kick-started by waste heat from the industrial plant next door, heat that would otherwise sail up the chimney.
In a power-hungry world, we need all the inventiveness we can get. Roger Harriman, BBC News, Slough.
That's actually the only recorded instance of Peter Dearman ever wearing personal protective equipment. So the Dearman engine, it's a novel, patented zero-emission engine that runs on liquid air or liquid nitrogen. The two big features that I think are relevant to this particular audience and to generally audiences around the world are that it will be low cost, low maintenance. We're here to make money, not necessarily to save the planet. If we happen to save the planet as a byproduct, that's helpful. It will obviously be low emission because the product, the exhaust is either nitrogen or air itself. First two applications we're working on, I'll explain these in a little more detail. One is a diesel hybrid, effectively a range extender, a peaking plant, which benefits from the very high waste heat recovery, and a refrigeration and cooling device. I think we get a lot of credibility for this development by the fact that the people who are developing it at the moment and taking it to a test engine status are Ricardo. Ricardo Engineering are probably the world's second largest engineering firm. They are most notable at the moment for having produced the McLaren MP412C engine, which I think is now, under its P1 guise, the world's fastest road car. We will have a test engine delivered by the end of this year, and we'll have a proof of concept vehicle driving around in the UK by the middle of next year. How does this work? Well, if you take 700 litres of air or thereabouts, and you cool it down using a standard industrial gases process, a standard refrigeration process, using waste or off-peak or in future renewable electricity, eventually that air condenses and becomes a liquid at minus 196 degrees centigrade. That can then be stored at atmospheric pressure. So this is not a compressed air car, this is a liquid air car. And that's very important because when you come to decide you need the power, either in the form of large-scale energy power generation, or in our case in the space of a small car or a small vehicle or a diesel engine, you regasify the liquid by warming it up slightly. If you do that in a confined space, then you get pressure, and that way you can do work. The beauty of this engine is its ability to harness low-grade waste heat. And by that I mean waste heat up to about 60 to 100 degrees C, which is otherwise, frankly, useless. This isn't, however, entirely new. Back in about 1898 in New York, there was a car, I think this is a picture of it, driving around running on liquid nitrogen. It had several problems, one of which was that its maximum speed was 3 miles an hour. And secondly, Henry Ford came along very shortly afterwards, and the diesel engine, which we have today, was born. One of the reasons we like liquid air, though, is because there's an awful lot of existing infrastructure. When we look at alternative fueled cars, be they battery-driven, be they hydrogen fuel cell, they have issues in terms of infrastructure. We don't have enough charging posts. We almost have probably almost no hydrogen refueling plants, whereas we have an existing infrastructure for industrial gases worldwide. Air is abundant. It's currently available without cost, although I suppose Chancellors of the Exchequer worldwide are probably looking at this. There is an existing infrastructure to support early adoption, so for field trials, that's readily available. We currently ship it around countries in tankers, in pipes. There's a very mature supply chain. We know that an industrial gas plant will last between 25 and 40 years. Storage is at low pressure, and that's very important. So if you look at the tank at the bottom there, that's probably stored at 2 or 3 bar. It's simply an insulated tank. It's like a large thermos flask. It's above ground. There's no geographical constraints on it. And there's no fuel combustion risk either. It's also 7 times more energy dense than compressed air by volume. So that's very important if you want to put it on a vehicle. So how does this work? Well, Peter's invention, and the reason that the car you saw earlier wasn't good and this will be good, is because Peter found the way to get the maximum amount of energy out of a set amount of liquid air or liquid nitrogen. This is a standard piston engine. So if you look at the figure on the left of the screen, on the return stroke up the piston, as you get towards top dead center, you put in a small amount of a heat exchange fluid, which is a water glycol mix, standard antifreeze. At top dead center, you then inject a very small amount, about half a gram of liquid air or liquid nitrogen, and the two are pretty much interchangeable. And the result is that you've got one fluid at 20 degrees C and one at minus 200 degrees C, and you get a very rapid expansion of the gas. In fact, the expansion we've measured to date suggests that the explosion, although it isn't actually, there's no ignition there, but the explosion looks like it's as powerful as a diesel engine, about 29,000 bar per second. The other beauty of this process is that on the way down on the power stroke, the cryogen continues to draw heat from the heat exchange fluid, which means you get a very even expansion and a continued expansion. And the bottom of the power stroke, the liquid is exhausted, it's recovered and reused, and the waste gas is simply expelled to the air. And to give you some idea of why the engineers got excited about this, we did some high-speed photography. And if you look at the slide here, what we've got is effectively the white area at the bottom is a clear plastic bucket, over which is filled with water at about 10 degrees C. And we injected about half a gram of liquid nitrogen into this. This whole slide takes in reality, took about 20 milliseconds. Takes a little longer. What you'll see, though, is the force of the explosion, and also the amount of water that's expelled from the top and side of the bucket. So that's the injection is finished now. And the black area is simply the expansion of the gas. You can see it just about see at the top of the screen, the water is starting to come out of the bucket. And at the top right-hand corner, which is about 8 inches above the bucket, you can see the water starting to splash out. So on the one hand, we've got a very interesting reaction. On the other hand, we've got a very expensive way of emptying a bucket. When we did this, that was done at 30 bar injection. When we injected it at 50 bar, it actually blew the whole of the bucket apart, which gave us the opportunity to use the Michael Caine line. You're only supposed to blow the bloody doors off. So the benefit of this invention, if you look at the blue line at the bottom, that's really where the old process was back in the late 19th century. That process was simply taking a load of the liquid, putting it into a tank, allowing it to boil off under pressure, and using it in the same way you'd use a steam engine. Peter's invention effectively more than trebled the power that you can get out of any given volume of the liquid. Why is this useful? Well, it's useful because you can use it under a number of circumstances, but particularly because you start at minus 200 degrees, the waste heat that you get off the radiator loop, which is a third of the energy that comes out of a litre of fuel, of diesel, can be reused. So one of our first applications is going to be a very high efficiency, low-grade waste heat recovery system. Now this is a demonstration of what's called Carnot Efficiency, which is effectively a proof of the maximum amount of waste heat, of energy that you can recover from waste heat out of a given volume of that waste heat. So if we start with a 300 kilowatt engine, which would be a fairly standard engine for a large tractor, for example, about 200 kilowatts of that of the power that's generated is actually wasted in the form of heat, either about half of that through the exhaust and about half through the radiator. If you try to take the radiator waste heat and turn that back into power using standard organic Rankine type cycle processes, because you're starting at 0 degrees, or maybe at ambient, maybe at 10, 15, 20 degrees C, and your top temperature is 100, you can only actually get 21%, a theoretical 21% back. If you start at minus 200, as we do, you can actually get 4 times as much waste heat back. And that's very exciting, because that gives you the opportunity to make your, potentially to make your diesel engine smaller, and thereby to save fuel. This really just demonstrates that in another way, and I don't really propose to go through it in any great detail because I think it's self-explanatory. So why is our engine different? Well, it's zero emission, it's safe at the point of use, it's zero emission at the point of use. I think that's particularly useful in an urban environment. I think it's particularly useful in the long term. I think it's probably less useful for purely economic gain. However, where it becomes very interesting economically is the ability to use this low-grade waste heat, and also to use the refrigeration and the cooling aspects of it as a byproduct. So, for example, if you're looking at a refrigeration unit, you can not only power the refrigeration unit using the liquid air, you can also use the exhaust from it to do the refrigeration itself. The other thing is that this is going to be a very standard-looking engine. If you took a liquid air engine into your local garage, he would recognize it as an internal combustion engine, just with a kind of odd injection system. So it's a piston engine. So it's made from standard materials. In fact, the first prototypes we're doing, we're simply buying an off-the-shelf Grizzly engine or something like that, or a small Honda 2-stroke engine, taking the head off and modifying that. So we're not having to reinvent the wheel. The other advantage is that there's no rare earth metals involved in this. We're not dependent upon China having a monopoly of anything. This stuff can be built in country and therefore is economically good for whoever decides to produce this. 3 possible uses, broadly speaking. You've got a high yield waste heat recovery system. We've got a standalone zero emission engine, which you could use, for example, in a forklift, and a very cost-effective and zero-emission combined power and cooling as a refrigeration unit. So the waste heat to power, which I think is, in the longer term, probably over a 3 to 5 year period, probably the most exciting process. It's low capital cost, It applies to large diesel engines. They could be either construction equipment, they could be delivery vehicles, they could be coaches, buses, tractors, anything which is a large diesel. We've done some modelling on this and suggest that we can look at a 2 to 3 year payback. Now, when you compare that with the equivalent for, and this is based on a London bus admittedly, when you compare that with a payback, for example, for a hybrid equivalent, which Transport for London are currently using, their payback period is 12 years, which if you've got a 7-year franchise, as most London bus companies have, is not much use. The incumbent solutions we're up against don't really look at the waste heat from the radiator loop. Those that do are getting 2 to 5% maximum back. We think we can get 25% back. So the impact modelling we've done, a lot of numbers on this slide is not much good for a large audience like this, but what I can tell you is that the way you would apply a waste heat to power recovery hybrid is to downsize your diesel engine. There's no way we're going to move away from diesel engines in my lifetime. The next 40 to 50 years, there is too much energy density in a litre of diesel. We can't replace that. What we can do, however, is accept that diesel engines are most efficient when they run at a reasonably constant speed. The reason we need a 300 kilowatt engine is because every now and again we needed to do a bit of excess work. For example, again, using the bus scenario, when it goes uphill. But for the most part, it's pootling along at 30 miles an hour and it doesn't need that. So if you could downsize your engine, you could reduce your fuel consumption, but you need something to deliver the peaks. The Dearman engine comes in, gives you the ability to deliver those peaks in a very efficient way. And by doing this slide really shows that if you deliver what we call practical downsizing, which is about a 40% downsize of your diesel engine, you can make something like a 25 to 30% saving, and that gives you payback in 2 to 3 years. We think that's pretty interesting. The other application that we're working on at the moment is a cooling and refrigeration one. We're very conscious that as the world industrializes, more people are coming into urban environments, we need to find a way of moving food from the field more efficiently and at lower cost and with lower emissions into the place where the people are. I guess that's particularly relevant to a country as large as Australia. One of the advantages that the system they use at the moment with by and large small diesel engines, they're very dirty. Interestingly, they're hardly ever regulated. So whilst the main engine of the truck may be regulated to death, the diesel engine you put on the reefer unit isn't. That will come in time. The fact is, however, that quite a lot of companies, certainly in Europe, have started to look at using nitrogen, liquid nitrogen, as a coolant. What they're not looking at, though, because we have the patent, is to use the power of the expansion phase, i.e. from liquid to gas, to provide the power to drive the engine for the reefer unit, and then use the cooling from that to provide the cooling element. Now, if you use the Dearman engine for this process, not only can you save about 50% of your diesel, but you can also get about an 80% saving of your CO2. And in time that becomes fairly interesting as well. So cooling refrigeration. We have zero-emission vehicle applications that are possible. I'm actually seeing the world's second largest forklift truck manufacturer in about 2 weeks' time. The issue with that, I think, is more that the competition from the fuel cell market and from the electric market is pretty fierce. And so as a small startup company, we're probably going to duck out of that one for the moment, unless anybody in this room wants to put up a few $100 million to help us. Fueling infrastructure is pretty important, and for field trial purposes, is one of our strengths. There is existing, one of the problems with many of the competitive zero-emission vehicle technologies is that it either takes a long time to refuel, i.e. with a battery it takes you somewhere between 4 and 8 hours, depending on who you believe. And secondly, with a hydrogen one, well, you have to spend about £5 million to build a refueling depot. If you want to refuel using liquid nitrogen, for example, you ring up BOC or Praxair or Air Liquide or Air Products, and you say, I'd like a tank delivered to my farm, to my factory or wherever. 48 hours later, they've delivered one, with a pump, and you can pump it at around 100 litres a minute, so that's not really a problem. So the conclusions we have are that we think we can compete in a number of markets. Zero emission engines, yes, we can compete. In time, who knows, there might be a zero emission, there might be a liquid air city car running around. Again, that's not in our time horizons. That's a 10, 15-year business, and for somebody who's got much deeper pockets than our current investors. Waste heat recovery from an internal combustion engine, I think, is very high priority. But the first priority is refrigeration, because we think we can do that as a retrofit, and we think we can have a product to market probably by the early part of 2016. We plan to be in our first development phase with a test engine, as I say, by the end of this year, with a test engine in a vehicle, actually as a prototype, effectively, by the middle of next year, and then in field trials in late 2014, running through 2015. So hopefully, if I was to be invited back here in a couple of years' time, I might be able to come with me, bring with me an actual test engine and show it to you. That's a hint, by the way, because I've enjoyed my time in Australia. Longer term, this slide only appears to, oh, I see, okay. Longer term, we have an interesting vision which I think allows us to incorporate renewable energy into the program in an efficient way. We're working with the University of Birmingham, and hopefully as a result of meetings last week with the University of Melbourne on small-scale liquefaction. The drawback at the moment for remote farming, for remote business, maybe mines, for example, is that it's not currently efficient to truck liquid nitrogen or liquid air cross-country. However, what you do have in Australia, what we have in less of in the UK, is sun. You have a lot of wind. We have a lot of wind in the UK. We still have a lot of hot air from Parliament. But if we can incorporate that on a smaller scale, so maybe instead of a 1,000-ton-a-day plant, maybe a 10, 20-ton-a-day plant on an efficient basis, with the wind, with the sun, then we can do two things. We can give you backup energy. We can give, because we can turn it back into power very easily using a small turbine. But we can also power your fleet of vehicles. And effectively, once you've bought the capital equipment, you then no longer have to worry about the cost of diesel going forward. Because ultimately, once you've produced it, then we can produce a zero-emission engine for your tractor and for your equipment. So I guess our timeline on this, as I said, is probably to have something, a product ready for market by 2016 for the refrigeration, maybe a year or so later for the waste heat recovery unit. That rather depends on our success in getting engagement with some of the large OEMs. We're having a lot of interest from a number of large companies at the moment. National Express coaches have been very engaged in the process. Sainsbury's, a large supermarket in the UK, is obviously very interested because they have an awful lot of waste heat issues. They have a lot of issues around standalone generation, another application that we can turn this device to. We're involved with Caterpillar and with JCB, not yet with John Deere, but I'm hopeful. I think that what we're trying to prove at the moment, we're trying to get data from these guys to understand how they use their equipment, so that we can then put that into our modelling and we can come back to them and say, here is an application that works in your example. We did it with the London buses. We proved that you could get a gain of between 25 and 58%. Those are really game-changing numbers for a lot of people. Finally, I just want to touch on the liquid air energy network. Because a lot of the issues that we confront are related to policy and the ability to be taken seriously by policymakers, governments, and official organisations, we asked a group of academics to write a report, academics actually and industry figures, to write a report on liquid air and say, if we look at the world of energy and energy vectors, i.e. storage media for energy. We've had hydrocarbons for a couple of 100 years and they've been very good, but ultimately they are, if not going to run out, they're certainly not going to help the planet. And they're going to be regulated and they're going to become more expensive. We know there's an awful lot of shale gas and shale oil in Australia, but you need the price to be $150 a barrel before you can get it out of the ground. So we asked them to look at that. We said, at the moment, we've got batteries and we've got fuel cells or hydrogen. And then we've got these two little companies, one which I represent today called the Dearman engine, and another one which I'm on the board of called the Highview, which is a large-scale energy storage business. And we don't really get parity. So we need people to look at liquid air and say, is this a viable storage medium? So they wrote this report, and for those of you who are interested, the liquidair.org.uk site has the full report, has a load of roundtables from Germany, Scotland, from some of the manufacturers and whatever, talking about the possibilities for this technology. There's a lot of people in Europe that are excited about this, and I've been over here talking to various people in Melbourne, in Hong Kong, and tomorrow I'm going to see some people in Brisbane to try and get people to accept that there is another way to go, that batteries, very good in my laptop, pretty good in my phone, not very good, they don't scale very well, and the Chinese own pretty much all the resources to make them. And when you build a battery or we import a battery, you're importing somebody else's technology. This technology can be built in Australia, it could be manufactured here from parts, delivered here as well. So I think it has great possibilities. Thank you very much.